Hey everyone, Big Mac here. Welcome back to part 3 of Let's Review some of my favorite Calculus 1 questions that I gave during the semester that I taught a Calculus 1 class. So we're going to look at Exam 3 right now. And Exam 3 covered a number of different topics that include determining more derivatives of functions like the sine, the cosine, your inverse trig functions, additional functions like that, as well as just more properties, understanding the notions of minimas, maximas, like the formal properties of these at this point, we start looking at the second derivative, that kind of stuff. So here was a set of true-false questions that I had from Exam 3. So these were all dealing with derivatives, optimization, those kinds of things. So here's the first one. If a function, f of x, has a local maximum at a certain value of x equaling a, then the inverse function of x has a minimum at that point. Is that true or is that false? Number 2, if we have a function g prime of t, so the derivative of g, suppose we know for a fact that the derivative of g is in between 1 and 2. It's always greater than 1 and at most 2. It's always at least 1 and at most 2. Suppose we're also given a starting point that when t is 0, g is 2012. Again, I wrote this test last year. So, given that information, is it possible for our particular point in g of 2012, is it possible for that point to be 55, Interstellar? Anyway, that's the second question. Here's the third one. If another function, f of x, has a local maximum at x equals 2, then it is also the global maximum in this tiny interval 1.99 to 2.01. So just because we have the local maximum at a certain point, is that guaranteed that it's the global maximum in a very tiny window frame? So for this particular exam, I allowed calculators. For these problems, I was hoping that students would be able to figure them out in at most 2.5 minutes per problem. These were kind of problems where I was hoping that students could just either visualize what's going on, maybe not necessarily derive everything out, but at least try and make some kind of intuitive sense to themselves. Oh, this has to be true, or no, there's no way this can be true. So let's go ahead and look at each of these three cases. The first one, if f of x has a local maximum, then the inverse has a local minimum? No way! No way! By definition, if we have a function that has a local maximum, then obviously it fails the horizontal line test for having an inverse function. The inverse function doesn't even really properly exist unless we define it as two separate functions. And even then, it's not going to have a minimum. It's not, it would have a special point maybe at y equals a, but absolutely not at x equals a. One thing that did annoy me a lot was a lot of students were confusing f the inverse, this notation for the inverse function of f, with the reciprocal of f of x. I actually had two separate problems. I had one where we had the notation here, f minus 1 of x for the inverse function, and then I had f of x in parentheses to the minus 1. And I had people asking me, are these the same one? No, they are definitely not. Number 2. So if we know that g of 0 is 2 in 2012, and our derivative is always between 1 and 2, let's just try and figure this out. If our derivative is a constant, then we know we have a linear function going on here. So if we start at the point 2012 and we wind up with a slope of 1, by the time t was 2012, our y value, our g value would be 4024. So that means that is the absolute smallest that g of 2012 could be. Likewise, since we know that our derivative is maxed out at 2, we can just take another linear equation and see how high that particular value goes. So if it had a slope of 2, then when t is 2012, then our g value would be 6036. And what do you know? 55 is in between these two values. So yeah, is there any way for us to actually know? Not by this information that's given, but it is possible that g of 2012 is 55.55. It could even be 55.555. Alright, for the last situation, if we have a local maximum at x equals 2, is that the global maximum necessarily? No, it is definitely not necessarily the global maximum. Just a simple picture here. I made it look symmetric, but it doesn't even have to do that. So of course, by definition, if there is a local maximum at a certain point, then we know that we're going to have the function decreasing everywhere around it. But, we never had to we never specified a specific width. It wasn't always necessarily a 0.1 area, 0.01. I mean, that thing can be as small as you need it to be. So the fact is, in between 1.99 and 2.01, a lot of things could happen. So in fact, so just because we have one local maximum at x equals 2, that does not guarantee for a function that is also the global maximum. For stuff like polynomials and trig functions, most trig functions probably is, but it is not necessarily. So how do students do on these questions? Mixed results. So most students did the best on number 2, the one where we had our g prime of t function between 1 and 2. So I think most people were able to recognize that it's got to be between like 4,000 and 6,000, so it could have been 55. Like I already mentioned, I had a lot of students who were confused with the first problem. Where's my mouse? There it is. The first problem, and confusing the notation for the inverse function with the reciprocal of the function. So that got me pretty upset. And then number 3, a lot of students were just like, yeah, it's got to be the same. Because in every example that we've looked at, they were the same. But again, when we define these things, we never specified a particular width. So it could have really gone either way. So, I don't know. I mean, these scores may be more suggestive of just random guessing. I honestly am not sure. But I just got the notion that students were not comfortable with either the terminology, the concepts of what a local maximum, what a global maximum is, the concept of what an inverse function of a graph looks like. Some of this stuff is pre-calculus prerequisites, so, some things that I don't necessarily go over, but I thought it was interesting to see where they were coming up with their misconceptions. Alright, so the last question that I'll talk about from this particular exam, this is one that I was kind of upset about, but I was upset about most of the questions because I wrote them and the students weren't getting them. But this is basically how I wrote it down. Find the derivative of this function. We have the hyperbolic cosine squared of x, and then we have minus e to the x minus e to the minus x all over 2, then that whole thing squared. Find the derivative of that. Simplify as much as possible. So students could use calculators, and ideally students would have solved this problem in 3 minutes, and even if it took them 5 minutes, I would have been okay with that. So what is going on? What is a hyperbolic cosine, and what is that? So what is that thing? So actually, the hyperbolic sine and cosine are two functions that we looked at that follow these particular definitions. The hyperbolic sine is e to the x minus e to the minus x over 2. We just saw that on the last question. And the hyperbolic cosine is the same thing, except we have a plus here in the middle. So the cool thing about these two functions is that if we take the derivatives of them, we just get the opposite. And we don't have to worry about minus signs or anything like that. So the derivative of hyperbolic sine is hyperbolic cosine. Derivative of hyperbolic cosine is just hyperbolic sine. That's all there is to that one. So recognizing that the second term was just the hyperbolic sine squared, I asked students to basically just find the derivative of this thing using chain rule. They could then say that the derivative of something squared is 2 times something times the derivative of that something. So from the hyperbolic cosine squared, that's derivative has got to be 2 hyperbolic cosine times its derivative of hyperbolic sine. Likewise, for hyperbolic sine squared, we have to take its derivative, so it's 2 times hyperbolic sine times the derivative of the inside part, so hyperbolic cosine. Well, what do you know? Everything cancels out. The answer is 0. Seriously, the answer is 0. So, of course, if we have a derivative of a function that is 0, what does that tell us? Well, I actually had a couple students recognize, wait, we saw this thing in class where you talked about a trig-like identity where you had the hyperbolic cosine squared minus the hyperbolic sine squared, then that was always equal to 1 for any value of x. And indeed, if you just, distributed out your e to the x's and your e to the minus x's and you just multiplied everything out in canceled terms, indeed, all you're left with is just 1. So I had a couple other students who were like, well, the derivative of a constant is 0. Done! And I was like, yes, you get full credit. So the only problem with this kind of problem was that students either got the answer like right away, as in they spent less than a minute on it, or they got stuck on something. So it could have been just, recognizing the definition of the hyperbolic sines and cosines. It could have been in trying to take the derivatives. It was a combination of everything. Because those that did not recognize the hyperbolic sine and the hyperbolic cosine definitions, when they tried to take the derivatives of the two parts, they messed up on the chain rule. So they really did not help their case at all in that situation either. So there were about 40% of people who were like, I got this. I would say they got the problem in less than a minute. The rest of them struggled. I had some students try to take 10 minutes on that problem, on a problem that's not supposed to take 10 minutes, and then the rest of them just kind of struggled through that one, and then wound up skipping into other problems. So, that'll be part 3 of my favorite calculus questions. So this is Big Mac saying, later.